So that went away. Excellent. So thanks for having me here. And continuing the theme, I'm going to talk about reduced formats in CMS. I'm going to take a slightly different tack and end up making a proposal. So this might be a little fun. So I also lead the Analysis Tools Task Force on CMS. And we asked a lot of people about what they use as their inputs and how they do their data analysis on CMS. And so you'll see a lot of these pie charts that we collected from trying to do a retrospective over run 2 as to how people actually got things done, because we're coming up with recommendations as to how to continue doing analysis effectively in the future and what tools to adopt, what patterns make sense. So just starting with the usual CMS analysis workflow, everyone starts from either AOD, MiniAOD, or NanoAOD, and you can see the rough breakdown of that in the bottom left. And you can see that these reduced formats, where AOD is somewhere 100 kilobytes per event or more, actually make up the majority of what we're using already. And we made this decision going back to MiniAOD nearly 5 to 8 years ago. And NanoAOD is more recent on the scene in the past 3 years or so, 3 to 4 years. And you'll see in a bit that it is also highly prevalent that people post-process their NanoAODs using this thing called NanoAOD tools, which is a PyRoot-based framework for doing data augmentation, essentially. And all that's done on CRAB or local batch. And then that gets thin, slimmed, analyzed, and then finally put into our statistics framework combined. Going into each of these data formats individually, so MiniAOD is a fairly intelligently slimmed down kind of classic experiment data format, and putting it in the context of what was just shown for Atlas, this is very, very similar to the DAOD that he was talking about. So you have all of the primary physics objects that you may expect. So isolated leptons, photons, jets, all of them are thinned with very inclusive cuts that allow you to do more or less any analysis, since except for a few % of them, we're covering basically everything as you saw from what we pulled from people. And the nice thing about MiniAOD is that it's we've figured out ways to make it very extensive in terms of what it covers, so that people can try to do exotic searches. And we have even low-level detector information that's stored for interesting objects. And the degree to which that information is stored is based on, or can be based on, how interesting that object is. So for instance, as a function of the photon PT or how isolated it is, we store different amounts of reconstructed hits around that photon, so that we can actually have fairly low-level information and supply that to more complex algorithms. We also store all of the particle flow candidates and tracks related to that. And this data format, now that it's fairly old, has been heavily appended to over the years and has grown in size because of that, from starting from around, I think, 20 kilobytes or so. But we've also figured out more clever ways to pack the data in the meantime. Figured out that in the very beginning, we also started from truncating mantissa for floating point numbers, so we get better compression. And we've ended up with a format that was fairly quickly adopted, still serves nearly half of the collaboration, and is also used to derive the NanoAOD that serves the majority of the rest. So for NanoAOD, again, this is a format that's about 2 kilobytes per event. These are flat N tuples with a very regular naming scheme for the columns and objects. So you have, what you might have cooked together as a graduate student in muon PT, et cetera, et cetera, et cetera, for all the other objects. And so everything that has the keyword muon in it belongs to a muon object. Construct this, you can turn this into a coherent analysis. As opposed to MiniAOD, the content of NanoAOD is very strictly monitored. The review process is fun. And it's done, of course, to try to stave off bloat, but we're greedy analysts. Bloat will always win. And eventually this is going to fail because of that. So At the end of the day, what we've got right now is something that's a total size of about 100 terabytes for all the data sets that we need in order to do any analysis on CMS. Sorry, all of the input data sets. Of course, someone's going to need some random detector variable, and they may have to go make their own. And there are also specializations that have come up that are not part of the mainline NanoAOD and not something that's widely proliferated throughout the collaboration that have full lists of particle flow candidates, tracks, hits on tracks, other very low-level detector information for doing studies, very similar to what was talked about in Atlas. It turns out we're doing largely the same things. And then one more recent player in the game is fairly detailed machine learning oriented truth information of various sorts, going down to even per hit J-on truth matching information, just speaking from personal experience. And yeah, you can see an example of all the different kinds of content that we keep. Right. And all the necessary things are there in order to follow the CMS model for doing, for calculating systematics and correction. So everything, the calibrated objects are stored. The inverse corrections to get back to the uncalibrated object are also stored, since that's usually near 1 and it compresses better. And then all of the information that you need in order to, excuse me, all the information that you need in order to derive systematics or calculate correction is also included in the NanoAOD. And this means that we have a fairly flexible format that can serve about 50% of the collaboration as things are. So when is this limited? So I think this is limited in particular due to the proliferation of private NanoAODs. And this comes from people wanting specific additions to their analysis that do not want to go through the review process of figuring out how to squeeze what they want into NanoAOD itself, or what they want simply can never fit. And so nearly half of NanoAOD is post-processed in some way. So that can be copied, skimmed, extended. And the fact that this is so prevalent within people using NanoAOD means that right now this is only sort of working because we have enough free space to support the post-processing. But this comes along with the message that it is clear that people want NanoAOD. And trying to understand this further in terms of how it's limited is going to be covered by Brian in the parallel session. So he'll bring a different perspective from what I'm about to do. Well, so how can we make this stay viable? So first question, of course, is what makes a viable, roughly common intuple in a general sense? So of course, you need all the physics objects. You can't make any presumptive cuts on physics objects. Carve yourself into a particular area of phase space aside from what your detector can measure. You need all the pertinent information to derive the systematics, and we've already got that in NanoAOD, or got that for the most part in NanoAOD. We have actually very extensive generator information in order to do that, and we cover things going out even into the WMAS, and in terms of systematics complexity. And you need to have usefully complete trigger and generator information, and keep the disk use light throughout all of that. And largely with NanoAOD as we have it right now, we have actually achieved that goal. So we have something that really does work, and people have decided that they need to add columns to this because what they see there is good and they only need a little delta, but they end up copying the whole tree, and you can see where this is going. So this is, of course, at tension with analysis specificity. You want to keep your own format slimmed and skimmed so that it is very, very easy to process data quickly. It's also, of course, at tension with people having new ideas, using the detector in new ways that we haven't thought of up until now. There's also trying to provide more and more information to machine learning and keeping more and more detailed information there so you can extract more discriminating power from the detector. And then finally, for doing physics object related studies, things like that, or track refits in time, you may need detailed or otherwise low-level detector info that can be very, very heavy when you want to append it to NanoAOD. So the only option really, and it's already been mentioned in the last talk, that lets you solve all these needs that we mentioned and diffuse the tensions as well. Oh, thank you. Is joins, so friend trees, and trying to write out only what you need and then put together only what you need in order to make a data format that makes sense. So this implies a large amount of bookkeeping that is presently missing from what we do. And I'm going to go through sort of proposing what a simplified version of this might look like. So you're asking me now, doesn't this look like Service X? Yeah, kind of. All right, so let's call it Lego AOD. And it would be, in this case, very prudent to try to figure out some sort of simple bookkeeping scheme by which you can take the core of NanoAOD and then label all the things that you could possibly add to it for a specific analysis in a way that you can actually bookkeep at scale, because scale is the problem here. And so you could, for instance, use the null hash to or use a null hash of SHA-1 or something like that to represent the core NanoAOD, and then you have hashes of the branch names in order to say, and a map for that in order to keep track of all the different flavors that you have. And you can follow a basic bookkeeping, like additional column data sets, never split the basic NanoAOD files, so that doing slicing is all you ever have to do in order to excuse me, in order to put your NanoAOD back together accurately so that your additional columns make sense. And then, of course, you can load those columns, join them in with Dask or friend trees, all the available technologies out there. And if you follow rules like this that are kind of simple, but simple and straightforward, but do the job, then you end up with a very easy way of putting together your events in a consistent way so that you make sure that all your derived data is useful. So this could indeed be a nice test bed for Service X. But you could also do this with CRAB, Dask, or even regular batch, so long as you're willing to do the bookkeeping in order to make this happen. And honestly, if we make this work in a simplified case, then going to all the grandiose heights of Service X and the things we want to do with that become much more possible because we have practice, which is always good. And maybe an achievable goal for this can be make this very simple implementation of doing joins and augmenting or going for kind of an augmented Lego bricks sort of setup for building NanoAOD so easy and so advantageous that we eliminate 80% of the full copy post-processing means that we've actually popularized the idea and at the same time significantly reduced private data proliferation. And if we can do that, then we're well on track for HLLHC. We've got something we can really work with. One major problem with this in this system or any other system that you're going to build is the fact that every time you open a file, you stand the risk of job failure. So you can't do this too much, or we have to make certain pieces of our infrastructure more robust. So concluding, CMS bases its success on generalized lightweight data tiers. Mini and Nano serve 85% of the collaborations analyses. The problem is that it's so popular and people like it so much that people add stuff to it and try to make it their own. And of course, this means that people like it and we did a good job, but this proliferation really cannot scale forever. So I think the way forward and the thing that we should practice and try to bring to the collaboration is something like this, kind of straw man Lego AOD idea, and see if we can actually build all the bookkeeping tools in order to put this together, and then provide ourselves a clear on-ramp for actually making use of more advanced tools we are developing right now. Thanks.
Sorry. Other questions on Zoom? Other questions in the room? Yes.
Hi, Lindsay. Yeah, thanks a lot. So, I mean, I think we're starting to see a pattern that might be like one of the outcomes of this analysis ecosystem workshop, this idea of kind of augmentation and kind of friend trees and so on. And because we're looking at like exactly the same thing. And so I'll give a talk about that in the other session. So it would be great to have actually some kind of input from CMS. One of the questions that I have, so like the post-processing that you say, it's not only post-processing that it's like wrangling the input, but it's also like back navigation that like adds some inputs from earlier data tiers and like adding like JANT hits and whatever. So when you say like 50% of the nano is post-process, so how, well, what fraction of that actually uses something kind of from earlier data tiers that is not in computable from nano content? Okay. Yeah, so Lindsay said it's not a large fraction, and okay. Yeah, so that sounds great. So for the Lego AOD, I had just one comment. So what in Atlas we're currently thinking is that, because you mentioned like this risk of failure for opening a file, like one intermediate step before going into this full, like, you're just, putting all your Lego bricks together willy-nilly, is what we're looking at is that you just produce friend trees in the main processing. You save all the friend trees in the same file. So you have the main tree and then a friend tree. And so this removes a bit of flexibility, but it, it's a little bit more stable probably and less bookkeeping because you have everything in a single file. So that might be an interesting kind of intermediate step.
So I just wanted to understand a little better, the what I've always heard from CMS is the NanoAOD around 80% of. Okay. 60%, but it sounds to me like it's only really 30% that are centrally produced, and the other 30% are. Okay, and what I was going to ask was, do you know about what factor increase in the space usage that are some of these are slimmed or thinned or whatever? I mean, Atlas can't always keep them straight, but they must be, some of them must be small subsets of. Do you know approximately increase in disk space that caused? Oh, sorry. Okay. That was very soft.